Good morning. This is the second of a series of webinar for Mathematica by Wolfram Research. Welcome everyone, all the attendees who have chosen to join us to follow Mark's session, which goes into a little bit more detail about the maths, how to actually do maths. I know the last webinar was how to get around the notebook and introduce you to the idea of interacting with the notebook. But this time we're actually going to do something on the screen, or Mark's going to do something that actually will help you with your studies. Just to let you know, everyone invited to the webinars will be receiving an email from Wolfram Research tomorrow with a discount offer for those individuals who want to use Mathematica for themselves for their studies. Please watch out for this email tomorrow, and there'll be a link, and then you'll be able to see what level of discount you will get for a Mathematica license. If you have any questions, then please go through your professors and they'll contact us directly. But sometime tomorrow you should see an email from Wolfram Research with all the details about the offer. And if you have any questions, then we can answer those for you. So yeah, today it's Mark, Maths and Statistics. That's why everyone is here. And Mark, I'll hand over to you if that's okay. And I think you have 1 hour, I believe, for this session. And enjoy. And there's the chat. So there's no poll today, but there is a chat. If you have questions, we'll log there. We'll do our best to answer the questions for you. Over to you, Mark.
Thank you very much, Tim. Good morning, everybody. Just want to start by saying that there is a questions panel on the side of your screen. Please feel free to type in your questions there as soon as you come up with them. I might not get to them straight away, but at least if they're there, we have a record of them so you don't forget them by the time it comes to the Q&A section. So as Tim has quite kindly pointed out, today is all about maths and statistics. We're assuming that you've done the Gen 101, so you'll have the basics, in which case it allows me to get started straight away. So without further ado, let us begin. So today I will be covering the following topics. They include points about numbers and precision, how they work in Mathematica, and how they may vary from other languages. A section about uncertainty. From a physics background, I understand that can be quite important. We then have points on symbolic and numerical calculations, and then finally we'll be finishing with probability and statistics and interpolation and a bit about fitting. As Tim has pointed out, we're going to be here for about an hour, so I hope you're all sitting comfortably. So to get started, I want to point out one of the unique points about the Wolfram language and how it handles different numerics in the language. And the first one is the fact that the Wolfram language has exact precision. So various computers and parts of bits of technology have limitations in terms of how accurate they can have their computations, and it's all to do with data sizes and how a computer handles memory. We're going to pretty much point out that the Wolfram language can ignore that to some degree. If you see on screen, I have a very straightforward equation of just simply doing the square root of 2x squared plus 2, and I'm aware if I nest that function 12 times, I get a pretty interesting result. What you'll notice is that this result currently contains x. However, even if I was to input a particular number in this case, I would still end up with a square root as the answer. The system will hold numerics as symbolically as possible until the last moment when a number is needed to be generated. It means that doing things such as simplify can be quite simple. Amusing, simplify, simple, never mind. But the point being is that even numerics such as pi are handled as a symbol until the last point where a number is requested. If a number is not requested, then you will get an exact symbolic answer at all times. This is the default we go for. We believe it's better for mathematics than trying to round everything to 16 decimal places for whatever particular reason. The next point then is, where did I get this 16 decimal places from? I've already mentioned it's to do with all to do with hardware, but essentially it's based on the fact that there is a limit to data handling within a computer. I'm not going to bore you with all the details, but the point is that this is referred to as machine precision, and it is roughly 16 decimal places. As you can see, it's in fact 15.9546. Why such an interesting number? Again, not going to bore you with the details. But what this does mean is that if a numerical answer is ever requested, we will always aim for the highest precision possible. To start with, this is primarily exact, but should you request it when a numerical answer is provided, it will go down to exactly 16 decimal places. The display version may be slightly different. So for example, in this case, we have only 5 decimal places, simply because the number is particularly large. However, that's a display preference, and you can change that in your options section of your Mathematica. There are other forms of precision that we can handle, and it's all thanks to that exact precision I mentioned at the beginning. Whilst 16 does give you a particularly nice answer, or suitable in some cases, it's not suitable for everybody, in which case we'd like to highlight that we have something we refer to as high precision, which means that you can specify the precision of a particular answer at any point. For example, you'll find that the precision by basic is 16 decimal places, as I mentioned previously. However, if you particularly wish to, you can specify this to higher, in which case here I'm setting the precision to 30 decimal places. Amusingly, you'll notice that again, the display is shorter, and that's because I've restricted my display in most cases to 16 decimal places. It's just the basic that Mathematica does, because trying to handle and display, say, hundreds of decimal places can be complicated in some cases. But I would like to highlight that set precision means that the calculation itself is at 30 decimal places, despite the visual representation. Something as simple as changing the order of evaluation can lead to some interesting effects, and it's the reason why we like to highlight that setting your own precision can have some very interesting results, in which case you may wish to set the precision based on whatever calculation you happen to be doing. If you need greater precision for whatever reason, then feel free to set that to 100 or greater. In most cases, we actually recommend that you stick to exact until the number at the end is requested. I mentioned, for example, pi is a very good example of this. The symbol pi itself is actually held entirely symbolically, and we have a method of calculating it to however many decimal places you choose. However, you'll find that when you force it to be a particular number, to start with, it does only stick to 16 decimals, as I mentioned. If you want to sit there and specify that you want it to however many decimal places you wish, then you can do. One thing I'd like to highlight is this exact machine and high precision gives you full control over the exact nature of the precision you use. And if you set it too early, you will find that it can adversely affect your calculations, in which case we always recommend using that kind of precision limiting towards the end, unless you have a particular hardware issue, and handling 100 decimal places might not be up to the capabilities of your noble PC. Along with precision comes uncertainty, I would say, in which case measuring things in the physical world is never exact. I would love it to be, but there's always a measure of uncertainty with all physical measurements, in which case we have 2 ways of handling this. We have the more recent addition, which is a better handling called around, which handles everything on a statistical approach, which is why when you ask for the addition of 10 with an around of 1, or 20 of an around with 1, instead of getting 30 plus or minus 2, you get 30 plus or minus 1.4. It's more of a statistical approach. In which case, plotting these kind of things on a graph, again, is just as simple. It's the same as plotting any other set of data you would normally use. However, the system handles the around appropriately and gives you these little error bars, for want of a better word. You'll find that this can also be done in multiple dimensions simply by changing the setup that the around function is wrapped around. So for example, in the previous one, around was only present on the x value, whereas here it's also present on the y value. And thus you get some appropriate error bars. These don't necessarily have to be bars, they can be all sorts of different shapes if you really wish to change those. The other alternative I mentioned for handling uncertainty would be what we refer to as interval. And this is a worst case basis, whereby a interval between 8 and 10 is essentially 9 with a plus or minus 1. Same with interval of 18 to 22, it's 20 with a plus or minus 2, which when you add the two intervals together, essentially comes up with the interval of 29 plus or minus 3, which is therefore appropriate to the previous calculation we've done. Again, adding these things to visualizations is fairly simple. You just specify the interval as part of the calculation instead of just a single functional value. This then brings me on to stepping slightly away from the numeric side of things and heading into algebra. I will quite happily highlight that taking a look at a polynomial such as this one and doing an expansion could take me a bit longer than I would necessarily like to admit, normally because I'm slightly out of practice, primarily because I can get the Wolfram language to do that expansion for me like so. As you can see, it can take not even a second. Doing things then such as collecting the like terms and taking a look at the coefficients is much simpler than it would be normally on paper. And I'm quite happy to say, because of the symbolic nature of the language, you can make this as pretty much as complex as you like, and in most cases, the reply will be fairly swift. If you want a list of all the coefficients, for example, you can change coefficient to coefficient list. Only difference is in this one, I'm specifying a particular item I'm looking for. However, here, I just want all of them. And you can see it handles it appropriately. Taking a look at finding the factors, again, would on pen and paper take me longer than I would care to admit, but here we already have an answer, faster than I can possibly explain that, to be honest with you. And then if at any point you wish to actually plug in a numerical value, we recommend using the replace all and rule setup from our previous webinar, in which case you'll find that you can now get a numerical answer based on the polynomial specified above. This then leads me into simplification, because handling polynomials and expanding them and finding their coefficients is all appropriate, but we kind of want to take it a step further. In which case we have simplify, which first off we'll start with taking a derivative of a rational function, just to show some nice complex mathematics ready for simplification. Earlier I used to a simple effect to highlight the capabilities of the exact precision. But here I'm highlighting that it doesn't matter necessarily how complex your system is. Simplify will attempt in some way to make that much more readable. The interesting point here is that the more complex your setup, sometimes the more time it will take you to do that calculation. However, Simplify has a significantly large amount of different methods put in there in order to make that as simple as possible. If you then want to start taking a look at doing things such as combining rational terms, again, you can take a look at the together function. In this case, you'll find that there's no other further processing that can be done in this case. If you, for some reason, want to take a look at showing the fundamental theorem of calculus, you can take a look at using the simple integrate setup. And again, you can simplify that as well. A partner to simplify would be the ability to solve inequations. Sorry, two words in one there. Solving equations and inequalities. There we go. You'll notice that the syntax for both of these is in fact identical. For example, here we have a set of a pair of equations, and we're just asking the system to solve those equations based on the values x and y, in which case it will now provide us with a series of solutions. In fact, we've got a set of 4 here. In which case we can also take a look at doing a similar thing with inequalities. Instead of specifying the two equations, we instead have a single equation and a set of inequalities. In which case, again, we're taking a look at x and y. By asking it to solve this, we then get to conditional expressions. What I would like to highlight, though, is that I'm specifically requesting for a solution within integer space. This can be changed to reals and complexes and so on and so forth. I just chose integers because it gave the most interesting output. Again, the output to this, as you see in all cases, is a list of rules. This can be changed to solutions just by simply using the replace all system that we've mentioned previously, in which case, first requesting your solution, and then using your replace all, or specifying the item you're replacing it with, and where from, you'll then find that you get an actual solution based on your replacement. Again, local behavior of a particular solution can be determined by using the series function, in which case it then gives you the regions over which these particular equations match. If you then wish to convert this to a normal expression, you can do. One thing I'd like to highlight is that this system is automatically handling complex numbers for you. It was mentioned in the previous webinar series, previous part of the webinar series, sorry, that complex numbers are handled also. One interesting thing then is the fact that reduce has more methods available than simplify. They can be used for similar effects, but not necessarily all the time, in which case I have to bring your attention to reduce as well. Here we're particularly asking for the reduction of a equation with an inequality, in which case you'll find that we get some very interesting results, which are imaginary in both cases. You'll notice that we have a very interesting representation of them, which is massively simplified over the actual result. I don't know about you guys, but having that particular result, which you can see when I hover my mouse over present on screen, would take up quite a bit of space and not necessarily provide me any greater information at the time. But then asking for a numerical result of those roots provides me more of a solution that I can personally use. One thing that will occasionally happen, or will happen quite often in fact, will be the fact that the results reduce provides will contain a number of conditions as opposed to just one. So here you can see there are two alternative solutions to this setup. At all points I've highlighted, the system will try to keep things as symbolic as possible, and it's the use of this function or notation of n at all times that will produce a numerical result. In which case, finding a specific numerical result for a numerical solution for this particular equation, you'll notice can be done. In which case, some of the results are in fact imaginary. Therefore, taking a look at finding the roots should be fairly simple. Plotting these on a complex plane, again, in most cases would be quite complex. However, asking a simple list plot of that same set of results, as you can see, is fairly simple. No further adjustments have to be made to the results before they can be plotted. It just goes down to the user to remember that the what I would normally refer to as the y-axis in this case is in fact imaginary. There is in fact a difference, however, between asking for n-solve and asking for the numerical results of a solve. What I'd like to highlight here is asking for the n-solve of that original equation. You'll notice gives us 5 results, the first of which, in fact, they're now pretty much identical. I probably shouldn't do this too many times, so bear with me a second. In fact, now they are identical. I seem to have chosen one equation where both effects are in fact the same. Normally these results can actually turn out completely different. Finding a numerical answer to a symbolic solution is not necessarily the same as finding a numerical answer to a numerical solution to the original equation. So I just wanted to warn you about that one. The difference is all about which is done first, whether it looks for a solution and then finds a numerical answer, or specifically looks for a numerical solution. I can imagine you guys are fully aware of the differences. One thing I'd like to highlight though is that n-solve tends to be faster in most cases than asking for a numerical result of an existing symbolic solution. That's primarily where I was heading with this, is if you do intend to come up with a numerical result at the end, I recommend taking a look at n-solve as opposed to solve and then asking for the numerics. When it comes to finding those solutions, roots tend to be particularly useful, in which case find root is a very, very flexible function which can handle a large variety of systems, not just simple ones like the cos one here, but can also be used for things such as two nonlinear equations and still provide you with a sensible set of roots. So those equations can be as simple or as complex as you like. All you need to do is take a look at the documentation in order to find out the differences between the syntax. This then brings me on to calculus, because this is the point where I normally start talking about things such as limits. Limits in the Wolfram language use the same syntax as rules, simply to keep things consistent so you can easily see the comparison between that which you would see on screen currently and that which you would normally write down with pen and paper. In which case, after specifying a limit, the system will quite happily handle things appropriately. One interesting thing is that left and right limits can be obtained as well using the option direction. This then brings me on to differentiation and integration. So many long words this morning. One thing I would like to highlight is that despite our normal tendency to specify a function in its full name, you'll find that differentiation, along with number or n, is just the symbol d in this case, in which case your differentials can be as complex or as simple as you like. In fact, in some cases, some individuals find it easier to take a look at the classroom palette to get the symbolic representation of differentiation as opposed to just simply using the function d. Entirely depends on your preferences to whether you prefer the visual method or the programming method. Same can be said with integration. However, in this case, we've used the full word, in which case they can be as simple or as complex as you like. One interesting ability of integrate, however, is the ability to take a look at the principal value and control whether or not to use the Cauchy principal value or not. In which case you'll find without that principal value, we get an error, which is deliberate. However, if we take a look at specifying, yes, we do want a principal value, the system then gives us an answer, a numerical answer in this case, as opposed to a symbolic one. Again, you'll find that our integrate setup tends to be entirely symbolic unless a numerical result is inevitable, in which case n integrate is also a function that may be of use to some individuals here. Works pretty much the exact same way syntactically as integrate. However, in this case, it will force everything to be a numerical approximation. One of the strengths of n integrate that the general integrate function does not have is the ability to handle things such as oscillatory integrals. There we go. Such as this one. Sadly, integrate itself doesn't necessarily have those capabilities. So when we now do the n integrate, you'll find I get a numerical solution. So the point to be made here specifically is that whilst integrate and differentiate do have a wide variety of capabilities, in some cases when a numerical answer is required, you can rely on the ability to just provide n at the beginning of the function name. This then brings me on to the idea of minimize and maximize. You'll find that anything minimize and maximize are handled pretty much exactly the same in terms of syntax. You can simply swap the word around, and from their name you can pretty much guess exactly what they do. So I'm not going to go through them in too much detail, apart from provide you a simple example on screen now. In which case you'll find that the minimization will provide you with a series of solutions, including the conditions required for them to be met. Again, numerical optimization is done separately in this case. As you can see from the previous example, these were all entirely symbolic. However, if you are looking for numerical solutions, again, it is as simple as just adding n to the beginning of the functionality. in which case it will now take a look at finding you those particular values with which the maximum can be found. So in this case, we're aware that the maximum value that can be obtained is 3.5, given that x is 1.93649 and y is 0.5. The difference in this case is that these are looking for global extrema. If you're taking a look for local, then you'll want to start with the functions find minimum and find maximum, simply because you can specify the start value with which to start the process. In which case, if I'm looking for a local minimum, here I'm specifying that I want to start my process from x equals 2, in which case you'll notice it finds a different minimum than the one above, than the maximum above. Obviously, it's minimum and maximum. I should have done the same function there, never mind. Serves me right. In which case I want to take a look at differential equations. The first one was one I've come across on many occasions, which will be the damp oscillator. In order to solve the damp oscillator, we first have to provide the set of equations required to describe that specific oscillation. And then in this case, I'm going to have to take a look at the function dsolve. In this case, you'll notice that it's not necessarily happy with the equation provided. However, if I tend to take a look at the plot, you may notice exactly why. In fact, that's not working either. That one should have worked. Just wondering if I've messed up the syntax. 1 second. No, that looks perfectly fine to me. Is there a value in t? There is a value in t, that's why. 2 seconds, I'm just going to clear t. In which case, this should now be handled appropriately. There we go. Serves me right. Should learn to clear t every time. It's normally x that's my problem. Anyway, here, as you can see, now that I've managed to clear t, everything is working appropriately. So we've found a symbolic solution to the damped oscillation equation, and then I can quite happily plot that on a set of axes. One thing I would like to take a look then is at the parametric plots in order to find a solution for the phase space. One thing you'll note is that without initial conditions, various constraints will be created. So if we don't provide the initial conditions in this case, the solution then provides me with the additional constraints. That's what the values C tend to represent. In which case, trying to find the various values of these particular constants is then down to the individual. Two things that come up quite heavily are ODEs and PDEs. So we'll quickly go through, I say quickly, we'll go through those now. The first one we'll touch on is the ODEs, simply because we're taking a look at the atmospheric convection as it results in a chaotic motion. So here I have a particular set of complex equations, which took me some time to wrap my head around, in which case, taking a look at the solution, you'll find doesn't necessarily provide me much more information because it's a result of 3 interpolation functions. Trying to visualize these was a particularly interesting challenge. However, I took a look at parametric plotting it to find that they do that automatically for me, in which case I get a very interesting diagram. I would like to highlight trying to do this on pen and paper took me far longer than I intended, so I gave up most of the part way through. So I will be honest with you there, which is why I prefer doing it with a Wolfram language. Which then brings me on to partial differential equations, something which I get asked about quite a lot as to, well, how does the Wolfram language handle them? The only requirement for partial differential equations in this case is that you specify each of the individual components as separate variables, in which case I can now, once those 3 things have been specified, request an ND solve of that particular set of partial differential equations, there we go, got there, given a set of parameters, or in this case, the space of which I'm taking a look at the result for. In this case, I'm aware that stiffness switching is the required method. If this method is left blank, the system will attempt to find an appropriate method for itself. Bit of nice automation there for you. However, I'm aware that for this particular set of partial differential equations, if you don't specify the method, it takes quite a bit longer to actually provide you an answer. in which case the results in this one can be quite happily visualized as a time evolution. This is taking a few seconds to evaluate still, even with the method provided. So this is an interesting one. When I show you the manipulate, you'll see exactly why. Maybe I do. Sorry, that was a comment from one of my colleagues. In which case, provided the manipulate, you can now see that I am quite happily able to manipulate the aspect t for it to provide me the graphical representation of what's going on. Something which I find a bit more relatable than the interpolation function provided otherwise. This then leads me on to my favorite section, probability and statistics. The reason I prefer this section is primarily because it's a bit more within my range of capabilities, and mostly because a lot of this is handled entirely symbolically. If we take a look at something as simple as the normal distribution, for example, even specifying that the item is stored symbolically, highlighting that it is a form of normal distribution with a mean of 0 and a variance of 1, in which case I can quite happily ask for the variance, the standard deviation, skewness, and so on. Taking a look at the probability density function and the cumulative density function quite easily. In fact, even taking a look at the quartiles. In which case you'll notice that, again, it's still handling most things symbolically. No numerical answers provided apart from those that are obviously numerical. But that's not the only thing you can take a look at doing with such a functionality. If at any point you wish to sample various values from that probability, you can do. Well, not that probability, that distribution. In which case this can quite easily be plotted just by asking for the probability density function of the histogram distribution of that particular random generated set of numbers. In which case, just to see how accurate this was, and decided it'd be a great idea to actually do a comparison between that and the initial normal distribution used. In which case you'll notice that the normal distribution used here does not have the 0 and 1 specified, as that is the standard understanding, the standard expectation of a normal distribution. And you notice it's done a pretty good job. I specifically chose 1,000 points in this case because I'm aware if I go too high, it can take quite a while. So that was taking a look at the original distribution and retrieving the numerical values from that. The alternative in this case would be to take some example of data that you would have retrieved or obtained as part of your calculations and take a look at determining what distribution matches that particular set of data. I'm going to use the random numbers I generated earlier, such that you can, just so that I can prove that the find distribution function will then determine that they did match a normal distribution. In this case, as you can see, the values are off ever so slightly. What I would like to then highlight is the fact that you can actually do a simple test to find out how likely it was that the distribution that was determined by the system automatically does in fact match your data. However, a single number is not necessarily enough to prove that that is indeed true. So therefore, we can take a look at the full hypothesis test. In which case, it gives me an item, which is referred to as the test data, and we can take a look at the full list of all the different data tables. So you can see all the list of all the different tests that were actually performed, the statistic that was actually provided, including the p-values appropriate for each one. If at any point I cannot be bothered and decide to just ask for a simple conclusion, the system will also provide me one of those as well. So at no point do I have to actually sit there and write that out. So in our case, the null hypothesis that the data is distributed according to the normal distribution is not rejected at a 5% level based on the Kramer von Mises test. And I'm aware I've probably mispronounced that, so I do apologize. So taking a look at doing this and putting it into practice, because I've highlighted that we can go from a set of data to a distribution, I thought it'd be interesting to take a look at something which is known to have a distribution to it, which is the statistics of the Old Faithful geyser. Here I've simply decided to provide you a histogram of the different wait times based on the probability density. To me, as simple as my understanding of statistics goes, that looks to be a combination of two different normal distributions to me. In which case, I thought I would create a mixture distribution, which is assembled from those two different setups. I am going to clear F, before I make a mistake. In which case, now that I'm assuming that to be true, I take a look at asking the system to find the parameters for that particular distribution such that it fits the data I have available. In which case, you'll now find that it's provided me all the different means and standard deviations for the two particular normal distribution that would then match that data set. So let's just check that according to the data. As you can see, it roughly does resemble the data. In which case, I probably should take a look at doing some tests to prove if my guess was even remotely correct. In which case, the probability in this case is quite low, sadly. So doing a random sampling of that particular distribution, the one which I've estimated is correct, and then asking for a test again, we'll find that no, that's a particularly small number. This was definitely not an accurate guess in my case. I think I can be forgiven for my simple understanding of statistics. But as you can see, it's quite simple. It's very simple and effective to go from a set of data to a distribution, in my case, a misdone guess of two normals, and find all the different parameters and prove or disprove as to how effective your particular, in my case, guess was. I can imagine some of you individuals out there would make more of an educated guess than I did. In which case, I want to highlight that, like the rest of the items I've been mentioning so far, all of this can be done entirely symbolically if you choose. In which case, you can just quite happily specify symbols instead of putting in the numerics. In which case, finding the probability or the expectation of a particular distribution based on a set of parameters, so in this case x squared, is pretty simple. I must highlight that yes, I chose a particularly simple distribution, a normal, something that most people can recognize. There are other distributions out there, in which case we do not mind if they tend to be discrete or continuous. For example, we quite happily handle Poisson distributions just as easily as we do viable distributions, including their different plots. Just an amusing idea, on the next page I decided it would be a great idea to try provide a complete list of all the different distributions we handle. However, you'll find that it tends to be a particularly large set, and sadly I was not able to give you an example of exactly all of them. This was the exact set up until version 12, which again added further distributions, so I will highlight and provide you a disclaimer. This is still not accurate because we keep adding more, so I do apologize. But then also I would highlight that's quite a lot of distributions and interesting points on statistics that you may wish to take a look at. Just as a small sample of some of those that were present on that graph, I wish to highlight some of the discrete and continuous ones available. Here is a small subset of them in order to try, as I would say, whet your appetite. If multivariate distributions, for example, are not necessarily your thing, you'll find that there are also simple ones that can be taken from sets of data, allowing you to use any set of experimental or live data that you tend to have. And not only that, we do also handle meta distributions as well. The only two I was able to understand in the time I had were truncated and censored. So there is an example of those here, in case you wish to take a look in more detail. For example, a truncated distribution is very simple. I've provided a normal distribution and provided the intervals or condition of the particular interval in question. In which case, as you can see, it provides me the probability density function and a very nice plot. Same can be done with a censored distribution, in which case I've chosen a left-hand censored distribution, simply because it allows me to provide you a nice little manipulator as well to go alongside it. So you can see that all the distributions, despite being vary quite considerably, are all handled fairly similarly in the Wolfram language. It does not matter how complex or how simple you wish the distribution itself to be, the handling and manipulation of them is always uniform and very simple. There's also a right-censored distribution in case you're interested. In which case I want to go into interpolation and fitting, and then I'll take a look at a questions and answer section just to make sure that there is, I have satisfied your interest, for want of a better way of putting it. in which case I will highlight this is a section where I got quite over my head quite quickly. However, I still wish to highlight that the interpolation capabilities of the Wolfram language are significant. This includes both non-linear and non-linear fitting capabilities. For example, if we take a look at doing an interpolation of this particular set of parameters, you'll find that an interpolation function is provided, which I can then query as I would using the part-based system highlighted in the previous section of the webinar. There we go. Derivatives are then also handled in a very fairly simple and to understand manner, in which case you'll notice that I'm using the regular expected short notation for differentiation as opposed to using the symbol D. Again, this interpolation can also then be used alongside ND-solve to represent a particular solution, if you choose. Fitting is also handled in a similarly simple manner, in which case providing a set of data and asking for a linear model fit provides me a particular fitted model for that set of prime numbers requested, which can quite easily be plotted. Non-linear model fit can then find the alternative in case that system is not necessarily linear, in which case you can see that the fitted model in this case provides me a logarithmic expression. And again, plotting that is fairly simple. If you prefer a symbolic form of the fitted functions, you can take a look at the function normal, in which case it will provide you, in this case, the comparison between the two different functionality. Thankfully, our little diagrams here have already highlighted that information for you, but this allows you to get the functionality out itself, such that outside of the model, such that further computations can then be done. If at any point you wish to take a look at various properties of the different fitted models, you can do. And I'll highlight, whilst I thought I found these amusing, I still do not necessarily understand the different values present. If for those who are your experts, and to be honest, in comparison with me, that would not necessarily take long, I would mention take a look at the documentation. There is a large amount of information in there which allows you to take a look at all the different properties to a surprising degree that are available for these particular fittings. This then leads me on to my questions and answers section. To start with, I'm going to take a look at the questions panel and see if there's any been submitted currently. After that, I have a series of content I wish to go through with you guys in case there's anything of further interest to you there. So bear with me while I do go silent for a moment, just while I quickly read the questions and see if there's anything I can answer at the moment. Does not look like we have any currently available, but please feel free to continue inputting any questions you do have into that questions panel. If they're not answered right now, they can be answered by email later on. They are all saved and we will get round to them. In which case, before we finish, I have a series of additional content I would like to provide to you guys for further interest. In which case, the first point, one I've mentioned on several occasions, is the documentation center. It is unbelievably extensive. In which case, I'd like to highlight that the documentation center itself, as I said, is quite extensive. But if you take a look at your symbolic and numerical calculations or simply data manipulation analysis, you'll find that a lot of the things I mentioned are already here, including optimization. Each of these then goes through guides and various functionality of which we may think you would be interested in, including find shortest tour, which sadly I couldn't put into this presentation. Oh, and Bayesian inference and statistics are also included, just as a side point there. And at all points they include tutorials and related guides on how to achieve various goals, which we believe are quite standard with our particular tool sets. So that is a very extensive set of documentation for you to take a look at, should you be interested in any of the functions mentioned previously today. If at any point you're looking for additional training on particular topics, I would mention taking a look at the Wolfram training calendar or training page. It's taking a few seconds to load on my system. But this particular web page you'll find contains a list of all of the Wolfram courses available to a particular individual. And are not necessarily limited to just mathematics, but they can go as in-depth or as simplistic as you like. These include video courses, which you can take in your own time, and classes, but there are also instructor-led courses which you'll find the schedules for available as well. In some cases, there are even archived special events for you to take a look at. So for example, I would recommend taking a look at the virtual conferences on PDEs and ODEs if they're of interest to you. But this is obviously, as I mentioned, is not just limited to mathematics, but I believe this would be the area of interest to most of you guys. If at any point you're interested in particular examples, say the latest and greatest of what Wolfram has to offer, then I'd recommend taking a look at the blogs, both for Wolfram and Wolfram Alpha, in which case they tend to provide some very interesting examples of the latest of our capabilities, especially when it comes to the addition of various integration or differentiational methods. If at any point you do have additional questions, and for whatever reason you have not got to the point of emailing your individual representative, you'll find that the Wolfram community is an additional place to ask these questions. One thing I will highlight is there is no question too silly or simple to ask. Please take a look at a variety of things that you'll find on there. Again, they're not necessarily just related to mathematics, but mathematics does tend to be one of the primary items present on there. There tends to be a lot of students or professors on there trying to determine if the latest method is in there, or if there is a particular reason why a solution to their dream equation is not available. So you will find a lot of people on there highlighting a lot of it, different parts of information for you. Another item I'd like to mention would be Wolfram Alpha quickly. It's our computational knowledge engine. I, for one, have had some great fun in this. It can be as complex or as simple as you like. For example, you can take a look at doing 3D structures and molecules, or if, like myself, your understanding of differential and integration equations is a bit more limited, you can simply ask Wolfram Alpha to do it for you, in which case it will provide you a step-by-step solution. Something I will recommend for you, especially when it comes down to coursework. However, I may or not have said that. If you prefer things that are a bit more amusing, in which case I'd take a look at some of the at home and at play examples provided here. I will highlight that Wolfram Alpha does know the answer to the ultimate question of life, the universe, and everything, and is indeed 42. Just as a bit of an amusement note for you there. If at any point you have not yet obtained yourself a Mathematica license, I would recommend that there is a section here on getting started with the Wolfram Programming Cloud, a non-download required version of Mathematica, which can get you started with all of the mathematical functionality. However, it is on the cloud. For some of the heavier duty maths, I would recommend getting a Mathematica license though. If at any point you are still unsure if Wolfram has the capabilities you're looking for, I would recommend taking a look at the demonstrations project. Primarily because a lot of these things are user submitted, in which case they will provide you examples of interesting demonstrations that we tend to use for various talks, etc. But as I said, they are user submitted, and each one comes with full information on exactly how it was implemented, allowing you to download an example or take a look at the source code that was used to generate it. So at no point do we leave you in the dark as to how it works. Again, these examples can be very extensive. The last two items I'd like to mention then, before I hand you back to my colleague Tim, would be, just in case you missed some of the details of the previous webinar section, I would recommend taking a look at the Quick Start Mathematics. It's a combination of the previous section and some of the more basics, which would essentially predate what we're currently talking about. It's more of the basics, but then getting on to workflows of how to obtain and achieve certain particular items, in which case the link can be found here. If, like some of my colleagues, you are more interested in the latest and greatest methods and capabilities, I'd take a look at our latest features section. In this case, I've provided you the link to the latest features in Mathematica 12. You'll find that in not too long of a time, there will be a latest features in Mathematica 12.1 as well when that release occurs. So that's my additional resources you may want to take a look at, and that's everything I have for today. I'm not sure if it's a good thing or a bad thing, but there has been no additional questions. If at any point you do have additional questions, then there is a follow-up email with which you can provide them. For now, however, I hand you over to my colleague Tim, and thank you very much for listening.
Thank you very much, Mark. Hopefully everyone on the webinar had some parts or even all of what Mark showed you helpful in how Mathematica and the Wolfram language can help you do the mundane part of math and then accelerate what you're trying to achieve, accelerate the path to a solution. And everything is copy and pastable within the notebook. Even the demonstrations website, there are more than 11,000 demonstrations. Wolfram has been around for more than 30 years, so 30 years worth of collecting demonstrations where you can have a look at the code, figure out how a specific solution was created, and the demonstrations are there for you to copy and paste. But there is also more to Mathematica than just math. There is lots of other areas that other people find, individuals find useful. Access to the Wolfram Alpha natural language queries within the notebook. If you want to know about a specific event or a temperature, Mark mentioned about your data sets being random numbers. How about instead of a random number, choosing the temperature of a city between two dates, a city of anywhere in the world, or weather data. So you're adding real data, and this is real data from Wolfram Alpha, to your calculations. So let me check on the questions, or if there are any questions. No. So thank you very much. I'm going to sign off in a few minutes. Please look for that email from Wolfram that will be in your inbox sometime tomorrow regarding the discounted license for Mathematica. There is a lot to explore, and we're here to help. The community, as Mark mentioned, you may not have to ask the question, just search. I would suggest using Google search because they've been doing search for a long time, and search our community, and more often than not, someone has already asked the question you're thinking to ask. And yes, we're here to help. Please visit the website and contact us, and you can also contact us through the teaching staff who will be using notebooks and the Wolfram language during their lessons. And I thank you for your participation within these two webinars, and hopefully we'll see you again soon on one of our other public webinars. If there is other areas you may be interested in, data science or 3D modeling or physics, then you're quite welcome to join us on those webinars also. And yeah, I think that's it. I think we will sign off now. Enjoy your day, and hopefully we'll see you sometime in the future. Thank you very much.